Hello everybody, I am Mika Seppälä. Archimedes, who is looking at us from the painting behind me, was concerned with such practical problems as computing volumes of solids and areas of domains. Here in this video we present some ideas that were familiar already to Archimedes to compute certain areas. And these ideas are the starting point for integration. The problem of trying to determine the area under the graph of a curve leads to the concept of definite integrals. This video is an introduction to definite integrals in a very special case, namely we will determine the area under a parabola. In this video we determine the area under the graph of the parabola y equals x squared and over the x-axis interval from 0 to 1. In the computation we need the formula summation k from 1 to n k squared, that is the sum 1 squared plus 2 squared plus 3 squared plus and so forth plus n squared equals n cubed over 3 plus n squared over 2 plus n over 6. This is valid for all positive integers n and can be derived by rather elementary considerations, which we will, however, not discuss in this video. There are other formula of the same type, namely summation k from 1 to n k equals n squared over 2 plus n over 2. This is the formula 1. The formula 2 is the one we need in our computations today. And the formula 3 is summation k from 1 to n k cubed, that equals n to the 4th over 4 plus n cubed over 2 plus n squared over 4. And finally, the formula summation k from 1 to n k to a power p, where p is a positive integer, is always of the form n to the power p plus 1 divided by p plus 1 plus lower order terms. This last observation is important when one wants to generalize the considerations that we present here for the parabola. Our task is to compute the area of the domain under the graph of a parabola and corresponding to given x interval. The idea that we use here is that we estimate the domain and therefore also its area by rectangles. For each rectangle we may compute the area easily. It is base times height. Here we have one such estimation. The graph of the parabola is the red curve shown here, and we fill the domain under the parabola by rectangles as well as we possibly can. Here we have used 10 rectangles. And as the number of the rectangles gets larger, the estimate gets better. And then we take a limit as the number n of rectangles goes towards the infinity. To make this more precise, let us first observe that when we decompose the interval from 0 to 1 into n subintervals of equal length, then each such subinterval has the length 1 over n, because the length of the interval from 0 to 1 is 1, and we have n subintervals of equal length. Therefore, the division points that decompose this interval from 0 to 1 into n subintervals of equal length for some given positive integer n, the division points are 0, 1 over n, 2 over n, and so forth. And for the kth interval, the division points are k minus 1 over n and k over n. As k eventually becomes n, then we have n over n, which is 1. So these are the bases of the rectangles shown here in this picture. So the kth rectangle has the base, the closed interval from k minus 1 over n to k over n. Its height is the value of the parabola at the left endpoint of this interval, that is, the height is k minus 1 over n squared. And the area of this rectangle, the kth rectangle, is base times height, and the base has the length 1 over n. Therefore the area is k minus 1 over n squared times 1 over n. This is the area of the kth rectangle. We add all these areas up, we get the sum, which we denote by small case s sub n, Sn, summation k from 1 to n, k minus 1 over n squared times 1 over n. So this is the combined area of the green rectangles shown here in this picture. And the green rectangles have been chosen in such a way that they lie entirely in the domain bounded by this parabola. Therefore, this means that the combined area of the green rectangles is less than the actual area of the domain. So this is our lower estimate, Sn, for the area of this domain. We replace the lower estimate rectangles, the ones shown here on the left, with higher ones to get an upper estimate. So we replace the lower estimate rectangles with rectangles whose height is the value of the function at the right endpoint of its base. So we consider the approximation shown here on the right. The kth rectangle in this approximation has the base k minus 1 over n, k over n, that is that closed interval. The height of this rectangle is the value of the function x squared at the right endpoint of this interval, that is, the height is k over n squared. And the area of the kth rectangle is therefore base times height, that is 1 over n times k over n squared. And the combined area of these green rectangles is the sum capital case S sub n, summation k from 1 to n, k over n squared times 1 over n. And clearly, the combined area of the green rectangles is larger than the actual area of the domain under the red curve, that is capital case Sn is larger than A. So this is our upper estimate for this domain. We have obtained a lower and an upper estimate. The lower estimate is lowercase sn and the upper estimate is capital case Sn. And the estimates are: the lowercase sn is summation k from 1 to n, k minus 1 over n squared times 1 over n. This is less than the actual area of the blue domain, and that domain, the area of that domain is still less than capital case S sub n, that is summation k from 1 to n, k over n squared times 1 over n. Let us take a closer look at these estimates, small case Sn and capital case Sn. We know that small case Sn is less than the actual area capital case A, which is less than capital case Sn. The estimate small case Sn is summation k from 1 to n, k minus 1 over n squared times 1 over n. And the estimate capital case Sn is k over n squared times 1 over n, and summation as k goes from 1 to n. We observe that almost all the terms of the sum on the left appear in the sum on the right, except for the first term. When k equals 1, k minus 1 over n is just 0 over n, which is 0, so the first term of the sum on the left is 0. That does not appear in the sum on the right. And conversely, the last term of the sum on the right corresponds to k being n, that is k over n squared times 1 over n, and if k is n, that amounts to just 1 over n, because k over n is 1. And that last term of the sum on the right does not appear in the sum on the left. So if we take the difference, capital case Sn minus small case Sn, that is summation k from 1 to n, k over n squared times 1 over n, minus summation k from 1 to n, k minus 1 over n squared times 1 over n, then almost all terms cancel out, except for the last term of the sum k from 1 to n, k over n squared times 1 over n. The last term corresponds to k being n, and then k over n is just 1, and 1 squared is 1, and therefore the last term of the sum k k from 1 to n, k over n squared times 1 over n is just 1 over n. We conclude that the difference of these estimates is 1 over n, and the limit of 1 over n as n goes to the infinity is 0. So the estimates capital case Sn and the estimate small case Sn have the same limit, and this limit is the actual area of the domain that we have to compute. Let us next compute that area, that is, we compute with the sum capital case Sn, summation k from 1 to n, k over n squared times 1 over n, and we observe that this can be written as 1 over n cubed times summation k from 1 to n k squared. This follows because every term in the sum, summation k from 1 to n, k over n squared times 1 over n, has n cubed in its denominator. So that can be taken outside as a common factor, and we get 1 over n cubed times summation k from 1 to n k squared. Next we use the formula. Summation k from 1 to n k squared equals n cubed over 3 plus n squared over 2 plus n over 6. And we plug that in place of the sum k from 1 to n k squared. We obtain that the capital case Sn is 1 over n cubed times n cubed over 3 plus n squared over 2 plus n over 6. By expanding the brackets, we get 1/3 plus 1 over 2 times n plus 1 over 6 times n squared. And then we take the limit as n goes to the infinity. And we know already that at the limit we get the area of the domain in question. And as n goes to the infinity, 1 over 2 times n goes to 0, and so does 1 over 6 times n squared. Therefore, the limit as n goes to the infinity of this capital case Sn is 1/3, and this is the actual area of the domain in question. So A equals 1/3. To determine the area of the domain under the parabola, we considered the sums capital case Sn, which is summation k from 1 to n, k over n squared times 1 over n, and we observed that the limit of these sums gives that area. Now, the limit of these sums as n goes to the infinity is the definite integral of the function x squared over the interval from 0 to 1. The notation for the definite integral is a modification of the summation symbol capital sigma. It's this kind of a long S. So definite integral from 0 to 1 x squared dx is the limit as n goes to the infinity of the sums of the type Sn. We have computed that this definite integral has the value 1 over 3. That is, the domain under the graph of the parabola y equals x squared, and over the x-axis interval from 0 to 1 has the area 1/3. Next we consider integrals from 0 to some arbitrary positive number b. So we consider, instead of the interval from 0 to 1, we consider the interval from 0 to b. And we defined that the definite integral from 0 to b of x squared dx is limit as n goes to the infinity of the corresponding sums. That is summation k from 1 to n, k times b over n squared times b over n. These sums have been formed just like the sums previously. That is, this sum here corresponds to the joint area of these green rectangles covering now the interval from 0 to b rather than the interval from 0 to 1. And this limit, that is this definite integral, gives the area under the parabola y equals x squared and over the interval from 0 to b. This area can be computed precisely using the same method as before for the interval from 0 to 1. Namely, summation k from 1 to n, k times b over n squared times b over n, can be written as b cubed over n cubed times summation k from 1 to n k squared, because every term in the sum has b cubed over n cubed as a factor. So these factors can be taken out of the summation, and we are left with summation k from 1 to n k squared. And as observed before, summation k from 1 to n k squared is n cubed over 3 plus n squared over 2 plus n over 6. Therefore, this sum k from 1 to n, k times b over n squared times b over n, is b cubed over n cubed times n cubed over 3 plus n squared over 2 plus n over 6. Now we may partly expand the brackets and move 1 over n cubed inside the brackets. So we get b cubed times n cubed over 3 times n cubed, that is just 1 over 3, plus 1 over 2 times n plus 1 over 6 times n squared. And this quantity has the limit b cubed over 3 as n goes to the infinity, and this limit b cubed over 3 is now the definite integral from 0 to b of x squared dx. We may further generalize this consideration. We may consider the definite integral from a to b of x squared dx. This is the area of the red domain indicated here in this picture. It is the area of the domain under the graph of the parabola y equals x squared and over the x-axis interval from a to b. Now, the area of this red domain is of course the area of the red domain together with the area of the white domain corresponding to interval from 0 to a, and then we subtract the same area again. So this is same as definite integral from 0 to b x squared dx minus definite integral from 0 to a x squared dx. We have already computed what is the definite integral from 0 to b x squared dx, that is just b cubed over 3, and in the same way the definite integral from 0 to a x squared dx is a cubed over 3, so we conclude that the definite integral from a to b x squared dx is simply b cubed over 3 minus a cubed over 3. The explicit computations presented here now tell us that if we defined a new function, capital case ft, as being the integral from a to a variable point t x squared dx, then this new function has the expression t cubed over 3 minus a cubed over 3. T is considered as a variable, a is a fixed point. The derivative of this new function, capital case f, is simply 3 times t squared over 3, that is just t squared. And we conclude that the derivative of the function capital case f is the function that we integrated when we defined the function capital case f. This is a deep observation. The concept of definite integrals can be generalized to all continuous functions using the same method presented here. And the observation just made is the first part of the fundamental theorem of calculus, which says that if f is a continuous function, then the function capital case f defined in terms of definite integral, so capital case f at a number x, is the integral from a to x f of t dt, that this function is an antiderivative of the function small case f. The result that the definite integral from a to b x squared dx equals a cubed over 3 minus b cubed over 3 was obtained using the definition of the definite integral and the formula summation k from 1 to n k squared equals n cubed over 3 plus n squared over 2 plus n over 6. For the sum of cubes, summation k from 1 to n k cubed, we have the formula n to the 4th over 4 plus n cubed over 2 plus n squared over 4. And that formula leads to the result that the definite integral from a to b x cubed dx equals a to the 4th over 4 minus b to the 4th over 4. Computation is precisely the same as the one presented here for the definite integral from a to b x squared dx. We may generalize that even further by using the observation that summation k from 1 to n k to the power p for a positive integer p is n to the power p plus 1 divided by p plus 1 plus lower order terms. And this yields the formula definite integral from a to b x to the power p dx equals a to the power p plus 1 divided by p plus 1 minus b to the power p plus 1 divided by p plus 1. Therefore, By these methods, we can compute definite integrals of all polynomials. Archimedes was able to compute areas of domains under parabola using methods like the ones presented here. He did that more than 2200 years ago. So in a way, he invented integration. He called it the method. But his inventions were forgotten, and integration had to be reinvented about 1800 years later. This picture here is a painting by Fetti representing Archimedes. This was painted in 1620.